For nearly a century, we have told ourselves a single story about the beginning of everything. A story of a single, infinitely dense point. A story of a cataclysmic explosion. A story of an expanding universe born from fire. We call it the Big Bang. It is the foundation of all modern cosmology, written in every textbook, taught in every classroom. But what if that story is wrong? Deep in the frozen void, a new eye has opened, the James Webb Space Telescope. It has stared deeper into the past than humanity has ever dared to look, to the very dawn of time. And the first whispers it is sending back across 13 billion years of darkness are not whispers of confirmation. They are screams of contradiction. Webb is finding things that should not exist. Galaxies more massive and more mature than our models could ever allow. Cosmic structures that formed in the blink of a geological eye. The universe, it seems, got a head start we never knew about. This data is so revolutionary, so impossible, it has thrown the world of cosmology into a state of quiet panic. The foundation is cracking. If you believe that science should follow the evidence, no matter where it leads, hit that like button and subscribe, because today we explore a theory that was once dismissed as heresy, a forgotten idea buried for 100 years that is now being resurrected by Webb's shocking new data. A theory that suggests there was no beginning, no explosion, and no expansion. Prepare yourselves. We begin. Something is fundamentally broken in our understanding of the early universe. To understand the crisis, you must first understand the timeline. According to the Big Bang model, the universe is 13.8 billion years old. For the first few 100 million years, it was a dark, chaotic place. Gravity worked slowly, methodically, pulling together clouds of hydrogen gas. It was a painstaking process. Our simulations are clear. The first small, infant galaxies should have taken at least 1 billion years to form. Massive, structured galaxies, like our own Milky Way, should have taken much, much longer. Then, Webb sent back the images. It pointed its golden eye to a patch of sky that looked like empty blackness, and it found them. 6 of them. 6 universe breakers. 6 massive, mature galaxies blazing in the ancient darkness, seen as they were when the universe was only 500 to 700 million years old. This is the cosmic equivalent of finding a fully grown oak tree just 3 weeks after planting the seed. It defies the laws of growth. These galaxies are titans, containing tens of billions of stars. To get that big, that fast, they would need to be forming hundreds of new stars every single year. For comparison, our Milky Way creates about 2 new stars per year. These ancient systems were stellar factories operating at a rate that our physics says is completely impossible in the early universe. Joel Leha, an astronomer who studied the objects, put it perfectly. We looked into the very early universe for the first time and discovered something so unexpected that it creates genuine problems for science. But the problem goes deeper. It isn't just about galaxies. It's about the very fabric of space itself. For decades, we have measured the expansion of the universe. When we measure it using nearby objects, we get one speed. When we measure it using the ancient light from the dawn of time, the cosmic microwave background, we get a completely different speed. This is the Hubble tension, and it is a cosmic nightmare. It's like a balloon being inflated, but the top half is stretching twice as fast as the bottom. The laws of physics demand that expansion should be the same everywhere. Yet our two most reliable methods of measurement give us two different answers. Webb's new hyper-precise data has just confirmed this contradiction is real. It is not a measurement error. Reality is behaving in a way our models cannot explain. These anomalies, these impossible galaxies, and this cosmic contradiction are not small adjustments. They are cracks in the very foundation of the Big Bang model. They force us to ask a terrifying question. What if we have been misinterpreting the most fundamental signal in the cosmos? What if the reddening of distant starlight is not a sign of expansion at all? To solve this cosmic puzzle, we must travel back in time, not to the beginning of the universe, but to 1929. While Edwin Hubble was discovering that distant galaxies appeared redder, a discovery that would become the bedrock of the Big Bang, another brilliant, eccentric astronomer named Fritz Zwicky proposed a different idea, a far stranger idea. He asked, what if the universe isn't expanding? What if light simply gets tired? This is the tired light hypothesis. It is a beautifully simple, elegant, and profoundly radical concept. It proposes that a photon, a particle of light, loses energy as it travels across billions of light years of space. Think of it like a bullet flying through water. The farther it goes, the more energy it loses and the slower it gets. For light, losing energy means its wavelength gets longer. It shifts towards the red end of the spectrum. A distant galaxy would appear red not because it is flying away from us, but simply because its light has grown weary and stretched out during its immense journey to reach our telescopes. The implications of this are staggering. If redshift is caused by tired light, then the universe is not expanding. And if the universe is not expanding, then there was no Big Bang, no single point of origin, no moment of creation. The universe could be static, eternal, infinitely old. The impossible galaxies that Webb discovered are no longer impossible in a tired light universe. The problem was never that they formed too fast. The problem was that the Big Bang model gave them too little time to form. In an infinitely old universe, they had all the time they needed. They could have spent 20 billion, 50 billion, or a trillion years slowly growing into the cosmic titans that Webb now sees. The universe breakers are not breaking the universe. They are breaking the Big Bang's strict timeline. This forgotten theory, once dismissed and ridiculed, suddenly solves the biggest mystery from the James Webb Telescope with breathtaking simplicity. It suggests that Webb is not seeing infant galaxies at the dawn of time, but is instead just seeing extremely distant galaxies in a universe that has always been here. If the tired light theory solves Webb's galaxy problem so perfectly, why was it abandoned? Why isn't it the leading model of the cosmos? Because in science, a theory must explain all the evidence. And there is one colossal piece of evidence that the Big Bang explains perfectly and which tired light has for decades struggled to address. It is the echo of creation, the afterglow of the fire that forged the universe, the cosmic microwave background. Turn an old television to a dead channel. About 1% of that static is a signal from the CMB. You are literally seeing the oldest light in the universe. This faint, cold radiation fills every inch of space, and it comes from every direction at once. It is a perfect thermal glow with a temperature of just 2.7 degrees above absolute zero. The Big Bang model predicted the CMB's existence decades before it was discovered. It is the leftover heat from the hot, dense state of the early universe. When the universe was 338,000 years old, it cooled enough to become transparent, releasing this flash of light
into the cosmos. As the universe expanded over 13 billion years, this light stretched and cooled into the faint microwave glow we see today. The CMB is the Big Bang's ultimate proof, its smoking gun. How does tired light explain this perfect, uniform thermal echo? The simple answer is it can't. In a static, tired light universe, this background radiation would have to come from the combined light of ancient, distant stars. But starlight is not thermal. And if that light were traveling for eons, losing energy, it would become blurred and smeared. The CMB should be a messy, uneven patchwork of ancient starlight. Instead, it is the smoothest, most perfect blackbody spectrum ever recorded in nature.
That journey leads us to an epoch of unimaginable energy density, the first microsecond of creation. We have always imagined a smooth, orderly unfolding from the Big Bang. But what if the beginning was not a single, uniform event, but an era of extreme physical chaos? Some physicists now theorize that the early universe was populated by a class of massive, non-luminous objects forged in the first fiery moments of existence, primordial black holes. These are not the astrophysical black holes we know, born from the collapse of massive stars. These are a distinct, hypothetical class of object, theorized to have formed directly from the collapse of overdense regions in the fabric of space-time when the universe was less than a second old. Trillions of them, with masses ranging from that of an asteroid to thousands of times the mass of our Sun, could have been scattered throughout the primordial plasma, acting as unseen gravitational anchors. They would have provided an alternative, rapid formation mechanism for galaxies. A primordial black hole with the mass of 10,000 suns would need no time to form. It was born that way. It would immediately begin to accrete the surrounding gas, acting as a pre-existing gravitational seed around which a galaxy could grow at an accelerated rate. The universe breakers Webb has found may not be galaxies that grew too fast. They may be galaxies that were simply assembled around a massive, pre-existing, non-baryonic core. This hypothesis changes the entire narrative of cosmic structure. It suggests that the vast cosmic web of galaxies we see today was not the result of a slow, patient process of gravitational clumping alone. Instead, its architecture may have been predetermined by a hidden scaffold of these primordial gravitational relics. We are not witnessing the initial birth of structure. We are witnessing the moment baryonic matter illuminated a framework that was already built in the dark. But this raises a critical question. If these massive, dense objects existed, why is the cosmic microwave background so impossibly smooth? How could a universe be both perfectly uniform on a large scale, yet contain these ultra-dense seeds of future galaxies? The leading explanation requires us to go back even further, to the first trillionth of a second, a theoretical period known as cosmic inflation. This theory posits that in its first instant, the universe underwent a period of exponential, hyper-accelerated expansion. It grew from a size smaller than a proton to macroscopic scales faster than the speed of light. This process would have acted like a cosmic reset, smoothing out any initial irregularities in spacetime, which explains the incredible uniformity of the CMB. But this process was not perfectly smooth. Quantum mechanics dictates that even in a vacuum, tiny energy fluctuations constantly emerge. During inflation, these microscopic quantum fluctuations would have been stretched to astronomical sizes. Some would have been stretched into the subtle 1 part in 100,000 temperature variations we see in the CMB. But other, rarer, higher amplitude fluctuations could have been stretched and compressed so intensely that they collapsed directly into matter and energy, forging those primordial black holes. So now, a new, more complex picture emerges. The universe was born in an inflationary event that both homogenized reality on the largest scales and simultaneously planted the dense gravitational seeds of all future structure. This would mean that every galaxy, every star, and every planet owes its existence to a random quantum fluctuation in the first infinitesimal moment of time. Our entire cosmos could be the macroscopic fossil of a quantum event. This revised timeline might also hold the key to the Hubble tension. If the early universe was populated with this exotic class of primordial objects and their surrounding halos, the process of cosmic expansion would not have been simple. The energy dynamics of such a universe, including accretion onto these objects and their potential decay, could have injected additional energy into the cosmic fluid. This would have altered the expansion rate in the early universe, giving it an extra kick compared to the expansion we measure today. We might be observing two different expansion rates because we are looking at two distinct cosmic epochs. The first is the early universe, whose expansion rate was influenced by the complex physics of this primordial population. The second is the modern universe, which has settled into a more predictable expansion after those initial conditions evolved away. The tension is not an error, it is an observational artifact of the universe's dynamic and violent youth.
This forces us to confront the most sacred law in all of cosmology, gravity itself. For over a century, our entire understanding of the cosmos has been built upon the foundation of Albert Einstein's general relativity. It is a masterpiece of a theory, predicting everything from the bending of starlight to the existence of black holes with flawless precision. But what if, on the scale of entire galaxies and across the span of cosmic history, it is incomplete? For 80 years we have filled the cosmos with a ghost, a phantom substance we call dark matter. We have never seen it. We have never detected it. Every experiment designed to capture a particle of this elusive material has come back empty-handed. Its existence is purely inferred, a necessary patch on Einstein's theory to explain a single, glaring observation. Galaxies are spinning too fast. According to general relativity, the stars on the outer edges of a spiral galaxy should be moving much slower than the stars near the center. Yet they are not. They move at nearly the same speed, as if some vast, invisible halo of mass is gripping them with extra gravity, preventing them from flying off into the void. We invented dark matter to be this invisible mass. But what if there is no phantom? What if the equations themselves are wrong? This is the basis of a radical alternative idea, a theory that suggests there is no dark matter at all. What if, in the profound emptiness of interstellar space, where acceleration is almost zero, gravity's grip does not weaken as we expect? What if the law itself changes, becoming fundamentally stronger over vast distances than Einstein's equations predict? This modification would rewrite cosmic history. In the tenuous, low-density gas clouds of the early universe, this enhanced gravity would have taken hold with ferocious strength. The slow, patient process of galaxy formation would be replaced by a period of rapid, accelerated collapse. Suddenly, the universe breakers are no longer breakers. They are the expected products of a cosmos governed by a more potent, long-range version of gravity. This idea elegantly solves the problem of Webb's impossible galaxies without inventing a single new particle. It suggests that the crisis lies not in the observations, but in our rigid adherence to a law that may be only an approximation. The universe, it seems, does not need a ghost in its machine. It simply follows a different set of rules in the dark. And yet this elegant solution creates a new paradox. While this modified gravity can explain the rotation of a single galaxy with stunning accuracy, it struggles to account for the behavior of entire galaxy clusters, where dark matter still seems to be required. More importantly, it cannot easily explain the precise pattern of fluctuations seen in the cosmic microwave background, the echo of creation itself. This ancient light appears to carry the distinct gravitational signature of dark matter from the universe's first moments. We are caught in a cosmic crossfire between two competing ideas: an invisible matter we cannot find, or a new law of gravity that is not yet complete. The universe is forcing us to choose between adding a new, mysterious character to our story or rewriting the very rules of the story itself. The data from Webb, by showing us a past that fits neither model perfectly, has only deepened the battlefield. This conflict pushes us toward an even stranger synthesis of ideas. What if both are partially right? Perhaps dark matter is real, but it is not a simple, passive particle. What if dark matter can exist in different states, much like how water can be ice, liquid, or vapor? In the dense environment of the early universe or the center of a galaxy, dark matter might behave like a fluid, a superfluid, with zero friction. This superfluid dark matter would form a flat, extended disk, perfectly mimicking the effects of modified gravity and explaining the rapid rotation of galaxies. At the same time, in the vast, empty spaces between galaxies, it would behave like normal particle-based dark matter, forming the massive halos needed to explain the behavior of galaxy clusters and the patterns in the CMB. The paradox vanishes, replaced by a single, unified substance with a complex, chameleon-like nature.
This leads us to a fundamental reassessment of the dark sector itself. We have always imagined dark matter as a simple, inert substance, a cosmic dust cloud whose only property is mass. But this new evidence suggests a reality that is far more complex and far more active. If dark matter can exhibit different phases or interact with itself, it is not a substance, it is a system. It possesses its own internal physics, its own set of rules, a dark chemistry operating on a cosmic scale. This is the core idea behind a leading-edge theory known as self-interacting dark matter, or SIDM. This model proposes that dark matter particles are not perfect ghosts that pass through one another. Instead, they can collide, they can scatter, they can exchange energy and momentum. While these interactions would be incredibly rare and weak, over the course of millions of years, they would fundamentally change the structure of the universe.
This simple addition solves one of the most persistent problems in astrophysics, the core cusp problem. Standard cold dark matter simulations predict that the centers of galaxies should have a sharp, dense spike of dark matter, a cusp. Yet, when we observe actual galaxies, we find their dark matter cores are much flatter and less dense, a core. In an SIDM universe, this is the natural outcome. The constant, gentle collisions between dark matter particles over eons would act like a heat source, smoothing out the central cusp into the exact flattened core that we observe. But the true power of this idea lies in what it does to the early universe. The ability to collide and scatter provides a mechanism for dark matter to dissipate energy. This is a game changer. In the standard model, dark matter can only clump together through the slow, inefficient process of gravity. But if dark matter can shed energy through self-interaction, it can cool and collapse into dense, gravitationally bound structures with shocking speed. The first halos would not need to form slowly. They could collapse catastrophically. Suddenly, the universe breakers seen by Webb are not just possible. They are the expected consequence of this more dynamic dark sector. The impossibly massive galaxies in the cosmic dawn are not a contradiction. They are the first beacons, built within gravitational wells that we dug faster and deeper than our old models could ever permit. The universe did not get a head start. It simply had a far more efficient construction crew, working with a set of physical laws we are only now beginning to decipher. This opens a conceptual door to an entirely new cosmos. If dark matter has one self-interaction, why not more? The dark sector might not be a single particle, but a rich and complex family of particles governed by its own set of dark forces. There could be a dark electromagnetism, with dark photons binding dark particles into dark atoms, forming structures that are completely invisible to us. The 95% of the universe we cannot see is not an empty void filled with a single boring substance. It could be a shadow reality, a parallel cosmos interwoven with our own, with its own chemistry, its own structures, and its own history, forever separated from us by the veil of its unique physical laws.